morning. So these are the brave ones that decided to return. You're free to discuss it amongst yourselves. You can talk about it with me. How did the exam go? Was it like easier than you expected? Harder than you expected? Like what was your reaction kind of walking out of the room? Was it easier? Significantly easier? You're kind of surprised maybe a little bit?
I was feeling kind of good about myself, which is now making me
Making you panic, right? Because, right? You weren't right?
What did I miss?
So, I mean, part of my goal here, right, is to I told you this, to over-prepare you on the homework, right? Right? Make the homework the hardest, right? Okay? And then see what you can do on the exams in 70 minutes, right? Like, it's pretty high pressure. You're going to find out tomorrow what your grades are. I know you've probably been used to teachers like either giving you your scores right away or having everything graded online and getting that green box right away, yes or no, I got it or I didn't. And believe me, I would love to give you exams that way, kind of just like your homework, right? Red box, green box, keep working on it, whatever, right? But we just don't have the infrastructure for that. But you're going to find out tomorrow. This is the way it is in my classes. I always wait until the lab after you take the exam to give you your scores back then. I don't post them on Canvas before that or any of that. So you can feel free to hate me for delaying the exam scores, but I do this very much on purpose. And you'll find out tomorrow a little bit why, and we'll explain the test autopsy and how I grade exams and all that sort of stuff. Quite frankly, you've been in the tutorial zone for the first 3 or 4 weeks of this class, right? This has really kind of all been tutorial. And today marks the day where we're going to send you out into the wider world, okay? And it's going to be brutal, okay? There's some boss monsters out there that are just going to whomp you. And it's not because I sit in my office and say, now I've got you trapped. Right? Okay, census is done, right? No. We're moving in, so we have talked so far about how things move. Like being able to predict where they're going to be and what their acceleration is or how fast they're going to be going after a certain time. Or that's all kinematics. That's how things move. What we're going to do for this unit is talk about why. And that question is an important one. Problem solving is still going to be there. We're going to fall back on a lot of these skills I've been teaching you. This stuff is harder. Like, by the time you're done with this, you're going to want to go back to kinematics and say, can we do that instead? Right? So there'll be times when you'll look back going, oh my gosh, I thought that was hard, and now I realize it's not as hard as it can be. So I'm just letting you know that, right? Just being very honest up front. You've got to keep doing what you're doing. And if what you're doing isn't enough, and you'll find out tomorrow whether or not it was enough, then changes need to be made. And now's the time to make those changes. Right? So there'll be lots of discussion tomorrow, lots of insight, all that sort of stuff. I'm also going to say this not to scare you or make you feel bad or anything like that, but again, just in full honesty. I know some of you are going to receive the lowest grade you've ever gotten on an exam. And how do I know that? I've had thousands of you tell me that. Mr. Bill, I don't understand. I'm a straight A student. Right? It's going to happen. Some of you are going to be very happy about the grades that you got on the exam. And whether you're happy or sad about a grade doesn't really depend on whether you got an A, B, or C. It's basically what sort of bar have you set for yourself, right? So in general, physics is very hard. The grades on exams tend not to be high. I'll just put it that way, right? So just be prepared. Don't go home and doom and gloom and as you talk with each other, oh, would you do this one on the front, right? And you convince yourself that you got every single problem wrong. Because that happens too, right? But just be aware, right, of the general trend. Students come in and go, what? How did we? but I'll be there. And there will be, counselors will be standing by tomorrow. I don't know about you, but this guy looks really freaky. Right? This is not the kind of guy that I would like to be alone in a room with. Right? Does anybody know who that is? That's Newton, okay? It's the odds, right? It's just kind of creepy, right? So, it's his fault. Not because he's creepy, but everything we're about to learn, right, really was brought together by Newton. Total genius, no doubt. But history records that he was also an absolute jerk. Like number one, didn't treat people right, okay? Worked really hard to suppress the careers of people that disagreed with him, okay? Didn't treat his servants well. So we tend to idolize and make heroes of the people that really pushed forward our technology. Newton pushed us forward, right? But that doesn't change the fact that he wasn't a very decent human being. Beyond that, he really wasn't into physics. This comes as a surprise to a lot of people because his name is just so synonymous with physics. And he did write what could be considered the Bible of physics, the first book that really brought together everything we knew and tried to explain why the universe is doing what it's doing. But Newton was more concerned with the end of the world. He was more concerned with finding the alchemist's stone. And this is not Harry Potter, this was real. Newton was an alchemist. In fact, he developed physics after being kicked out of college. That wasn't his fault. The Black Plague happened, right? Okay, so imagine the pandemic happens and we tell you that the school is closed, which it kind of was, right? And we all went online. But instead of having online classes, you get to go home and do whatever you want for 3 years, right? How about you? I go home and play video games, right? Okay, but like Newton sat down and decided he was going to figure out how the universe worked. About a year into that, he discovered that math at the time wasn't sufficient for explaining what he wanted to explain, so he just kind of invented calculus as a tangent, right? And then went back to school and tried to, do mercury and iron and alchemist stone stuff and figure out how the world was going to end. Nostradamus is one of Newton's favorite people. And then, like 20 years later, Edmund Halley of Halley's Comet fame comes to Newton and says, look, I got drunk last night in the bar and I made a bet and I'm not sure I can answer it. This is, 1700s London. I made a bet that the orbits of the planets are ellipses, not circles. Sounds like the kind of thing you would bet on, right? Okay. And Newton says, oh yeah, well I proved that 20 years ago. And Halley was like, really? Can I see it? And Newton's like, yeah, sure, I've got it right here. Well, he had lost it. He had lost physics. He had lost everything I'm about to teach you, right? And Halley was crushed. And Halley's like, well, can you do it again? And Newton's like, sure. And so Newton spent the next 2 years putting it all back together. Yeah. Genius, absolutely. But certainly came with a price to his social graces and his ideas of how he should treat people. So, we are going to dive into the ramifications of what happened here. Now, Newton discovered some things, and I'm going to give you these three laws of motion. There was 4 things that came out of his sort of mind about how the universe worked. We'll get to gravitation in the next chapter. Okay, so we're going to push that one aside. We're going to focus on the 3 laws of motion. I know you've heard these laws in some variation before, okay? And if you've read the book before coming to class today, you will definitely have been familiarized with these laws. I'm going to do this in the order of 1, 3, and then 2. Because it's the second law we're actually going to spend the most time on, okay? They all work together, but they are fundamental statements about how the universe works. And just as a side note and a tangent, make sure you understand, when a scientist says that something is a law, what do we mean?
It's true.
Okay, how do you know when something's true?
It's like an observation of the world.
So, the philosophers get into what's true or not. In science, we're pretty sure we know something is true when it works, right? The evidence is there, we have the data. And there's this pop culture idea of kind of maybe how science works, where you start with maybe a hypothesis, and then that gets turned into a theory, and if theory survives for a long time, it turns into a law. That's not right, okay? A law is a statement, it's an observation, it's this is what happens in the universe, okay? It's not a theory in the sense that it's been tested a lot and shown to be proven. It's a fundamental statement, a relationship between things or what's going on. So we reserve that term law. Newton's laws are not things that you go out and derive, I guess is what I'm trying to say. Like physicists like to derive equations and derive relationships between things. Those aren't laws, okay? You don't derive Newton's equations. You look at them, you test them, and you realize, oh, this is explaining something fundamental about how the universe works.
Why is that you can't derive?
Because, I mean, if you ask me to derive Newton's second law, I can't do it, because Newton's second law tells me the relationship between force, mass, and acceleration. It's where you start. I can derive other things from it. I can get all of the kinematic equations out of that. Kinematic equations aren't laws. They're results of applying the laws in the first place. So, yeah, it's one of those things that science, we don't communicate very well. We understand it because we go through it, but we could do a better job of explaining to people what's going on. So, let's talk about Newton's first law. Is anybody familiar with it? Anybody want to take a stab at what Newton's first law? Yeah, go ahead.
An object in motion tends to stay in motion.
All right.
An object at rest tends to stay at rest unless acted on by an outside force.
It's the unless part that's really important. I mean, the first statement is, is the binder going to go anywhere? Like, is it going to spontaneously start jumping up and down on the table? No. It wants to maintain its state of motion. And this is where we start getting into, wait a second, Mr. Balogh, the book isn't moving, the binder isn't moving. Well, actually, yes it is. We tend to think of movement as it's got to be going somewhere, right? But it has a state of motion. It just happens to be the state of motion where it's not moving, right? Okay? And so we need to be a little bit careful, right, about we move by motion, which is why the first law, I think, has those two first parts to it. An object at rest will stay at rest, but an object in motion, it's like we're trying to help people who aren't physicists, right, okay, distinguish what's going on here. But what's the unless?
Unless acted by an outside force.
Okay. What's a force? Not the force. That's different, right? But what's a force? Yeah, one.
Pressure, pull, and object.
Thank you. Thank you. That's it. Right there. Don't make it any harder than it needs to be. Okay? A force is a push or a pull. If an object is experiencing a push or a pull, it's experiencing a force. So Newton's first law, we need to, in order to change the motion, right? That's kind of the implied part. Something stays at rest or it keeps moving unless a force comes along to change that motion. Newton's first law lays down the idea that forces are required to change motion. If I take my tennis ball, right, and I throw it, It's in motion, right? But is this ball's motion changing the entire time it's in the air? What is motion? From what we've studied so far, position, velocity, and acceleration, which of those three things is motion?
Velocity?
I heard some uncertainty out there, but just good. Strong and wrong, right? It's velocity. Velocity is motion. Something that has velocity has motion. And the special case of no velocity being the case of rest. What is change in motion? Good, it's acceleration. And how did you know that? If velocity is motion, then to change the motion, something must be accelerating. Newton's first law is trying to tell us something. It's trying to tell us that in order for something to change its motion, there must be a what? A force, a push or a pull. So this ball, is it changing its velocity the entire time it's in the air? Yes, it's slowing down on the way up, right? And it's speeding up on the way down. The speed is not the same everywhere, right? So, this ball is accelerating, and if it's changing its motion, it must be experiencing a force. And what force is it experiencing?
Gravity.
And we've kind of come full circle, right? Question?
Oh no, I was saying after tossing the ball as a force.
Okay, and now, before, right, I was always like, ignore the hand, right? We're only going to talk about it while it's in the air. But now, can I push on the ball? Yeah. And is that push going to take the ball from rest to a state of motion? Absolutely. So now we can start talking about the pushing and the pulls that we can do on other objects. There's a device in your car that's designed to keep your car in motion and not change its motion. Can you tell me what device that is? The cruise control. What's the job of the cruise control? Keep the same speed. In other words, to make the acceleration zero. Can you be going 60 miles an hour on the freeway with cruise control and have zero acceleration? Yeah. But without the cruise control, what happens if you take your foot off of the gas? Start to slow down. So if we just broke Newton's first law, I thought Newton's first law says an object in motion wants to stay in motion. Your car is moving. We take the foot off the gas, car slows down. Nobel Prize. What's wrong here? Yeah, it.
The car is also being acted on things like wind, air resistance, traction of the tires.
There's a whole bunch of other forces, right? But if it were physics world, and the car were in outer space, right? If we took away all of the outside forces that were acting on that car, we could keep going, right? Do rockets, after they've left the Earth's atmosphere, do they need to continually be pushed on in order to move? No. We can give them an impulse, and boom, they'll keep going at that speed as long as they're not pulled on by gravity or anything else. So let's, okay, so there is a term that is associated with Newton's first law, and it's called inertia. Okay? Sometimes the first law is called the law of inertia. And inertia is one of those weird things that's defined by what it isn't. Inertia is an object's resistance to changing its motion. What has more inertia? A bicycle or a car? A car. Why? How do you know the car has more inertia? Okay, we haven't talked about weight yet. Nobody say the M word, because we haven't talked about the M word yet. How do you know the car has more inertia? If you apply a force to the bike, and then you apply that same force to a car, which one will change its motion more? Bike. So what does that mean about the bike's inertia? It's less. You see what I mean by it's like defined by the thing that it isn't, right? And I know, Mr. Balogh, why aren't you just talking about weight and mass? Because those aren't what you think they are. Okay, we'll get there. Oh, yeah, okay. I have to do this one on video because they would not buy me a set of china. Alright, I put stuff in the budget, they're like, can't you just eat on plates like everybody else?
We'll try to remove the tablecloth from under these dishes without making a mess. How? By yanking the cloth out very fast.
That was slow.
Pull slowly and the table setting moves.
Okay.
This will have to be done much more quickly.
Candle, very important.
The metal tube wrapped inside the loose edge of the cloth provides a firm grip for a fast pull. When the cloth is yanked out fast, the dishes barely move.
Alright, before you go try this at home, okay? Careful notes right here. Did you see what was in the edge of the tablecloth? It was like a pole or a bar or something like that, okay? That's critical for making this work, okay? You need the entire tablecloth to move at the same time in the same direction. If you just grab the tablecloth and try to pull, you're gonna get a whole bunch of different vectors and different parts of the tablecloth will be moving at different speeds and all the dishes are just gonna come together and crash, okay, right? So don't try this at home, but if you're foolish enough to try this at home, it'll work, it's science, right? But make sure you get a broom handle or something in the edge of the tablecloth. Why did the dishes stay put? What does Newton's first law tell us? What do objects at rest want to do? She's going to stay at rest, right? Okay. But the tablecloth was able to pull on the dishes. Before he pulled it out fast, he pulled it slowly, right? We'll talk about friction later. But sometimes there isn't enough time for forces. That's not quite true. The rate at which forces act on things can raise and lower the friction values. But the point of the video there was to show you that, objects like plates, they want to stay where they are. That's what they want to do, right? Whatever motion they have, they want to keep it. And that's kind of the basis of Newton's first law. Okay, Newton's third law. All right, so anybody want to take a stab at this one?
What about the second law?
We'll get there. We're saving that one for later.
It's like you pull that way and pull the opposite way.
Oh, good. I like how you said that. Because textbooks always just make this harder than it needs to be. For every action, there is an equal and opposite reaction. Okay, yeah. You punch me, I'll punch you. That term action, I really don't like it. It's kind of how Newton first talked about it, but forces always exist in pairs. Newton's third law is, right, for every force that gets applied to something, that thing pushes back, right, or pulls back. For every action, there's an equal yet opposite reaction. Equal in magnitude, equal in strength. Opposite in what?
Direction?
What does this mean a force is? It's a vector, right? So now maybe you're starting to see how bad this can get. Okay, but before we get there in the scary hat, we'll put the scary hat away for now. Okay, we'll get there, right? Okay, so this is what I want you to do, okay? I want you to take your index finger, okay? And I want you to turn to the person next to you, ask their permission, okay? And when you get their permission, I would like you to poke them in the shoulder and then let them do the reverse to you. Go. What'd you just experience?
Awkwardness.
Yeah, awkwardness, right? It's very, very awkward. So, I feel good, right? It just, but what happened? What did you apply? Force. Pressure. We'll get to pressure later, right? Okay, but you applied a force, right? Now, when you went in to poke that person and you poked them with too much force, not enough. Depends on the individual, I guess, right? Okay. How much force did they apply back? Mr. Balogh, I poked them gently, but they poked me really hard. Okay, no, right? When we apply Newton's third law, it has to be in that interaction, right? So if you poke them, they poke back, not with their finger, right, but with their toe, right? With exactly the same force. Now they might turn around and go, oh, that hurt, right? That's different. That's a different set of action reactions. But key to this experiment, what did you need? In order for the force to exist, you needed another person, another object. How many objects were involved in the interaction? 2. This is why I like to say that Newton's third law is the law where you can't pick yourself up. I need a volunteer. Somebody who thinks that they can lift about 170 pounds. Come on up. Thomas, right?
Yeah.
You good? You got medical insurance?
Yes or no?
Okay, alright. You please pick yourself up.
Good question.
Yeah, it is a very decent question.
No, just tell
We can't, but you're not trying here. Oh, okay, well, right. At the end of the day, you pushed on the floor. That was 2 objects. Pick yourself up. It's not gonna work, is it? Okay, can you pick me up? Okay, then everybody give Thomas a hand. So why was Thomas able to pick me up? Why can't you pick yourself up? How many objects do we have here? Just 1. But Thomas was able to pick me up because there were 2 objects, right? He applied a force up on me. What did I do? Force down on him. No comment as to how much it was, right? But you need 2 objects.
Stop me if this is a can of worms, but on a physics level, what differentiates one object from another?
Yeah, that is a can of worms.
Never mind.
Okay? Because they're like, well, Mr. Balogh, if I take my fist, I go, oh, right? Okay. Yes, those are 2 objects, your head and your fist, right? But overall, I cannot change the motion of my body by applying forces to my body, right? I can knock myself out and fall down, but that's gravity pulling on me, right? Okay? You can't lift yourself up. But like, what if you're like climbing a ladder or a rope? Isn't that lifting yourself up?
Pulling on the ladder.
You're interacting with another object, right? I cannot apply a force to myself to change my state of motion. I have to get another object involved in some way, shape, or form.
What would birds flying be considered?
They're pushing against the air. Or magic. So this can be like, how do you make sure that you are like remembering these things? Well, over the years, I've developed several methods for guaranteeing that my students will never misunderstand Newton's third law. And chief among those techniques, I would love to share with you, but I can't. Unless you promise me something. But I can't tell you what the method is until after you promise me something. So, are you willing to take the, I can guarantee you that you will never forget. Newton's third law. Guaranteed. Okay? It's also not indecent. Okay? But that's all I can tell you before you have to promise me that you will do exactly what I tell you to do for like the next 2.5 minutes.
Yeah.
Yeah, you trust me enough?
Yeah.
Okay, I'm not gonna lead you astray. Let's close the doors. We don't want this to get out.
That's a cool start.
Yeah, let's close the doors. Okay? And for those of you that are saying, no, don't let this happen, you didn't speak up, so it's your fault. Okay? Thank you, Brandon. Okay, right? Now, do you promise to do exactly what I tell you for the next 2.5 minutes? Everybody has to do this. You ready? Raise your right hand. I solemnly say, okay, no, we won't do it that way. Okay? I am going to teach you the Newton's third law song, and then all of you are going to sing it. Some of you want to run now, don't you? Okay? But you promise. Okay? Nobody else is going to know about this. Ignore YouTube. Nobody else is going to know about this. Right? Okay? It's okay. But I'll explain later why this is guaranteed, why you will never forget. Okay? So, the Newton's third law song is a reminder of the number of objects that are involved and how they're interacting with each other. So, let's do, give me 2 objects that are interacting. The what? Didn't hear you.
Paper in your fist.
Paper in my fist. Like that?
Sure.
Okay. Paper in my fist. Right? Okay. This is how I would sing the Newton's third law song to make sure that I never forget that there's 2 objects and how they're interacting. I will sing it for you. Those of you who are still conscious after I am done singing will repeat the song. You ready? And I'm gonna let's see. I'm gonna sing fist first. All right, here we go. If my fist exerts a force upon the paper, then the paper exerts a force upon the fist. That was your opportunity to clap and get in there. No, it's too late. It's too late. Okay, right? But you ready to sing now? Sing fist first. Ready, go. If the fist exerts a force upon the paper, then the... Okay, you guys are awful. You guys are just... Okay, wait. So, I'm guessing many of you have never been to Africa either. Okay? But in many countries, especially Africa, people sing. It's just a part of the culture. And they sing with their hearts. They sing with their souls. It doesn't matter how good or bad they are. They just sing. Let it rip. Your best in the shower, impersonations, Taylor Swift, whatever, okay? Let's let it go. Nobody else will know. It's okay. It's okay. You ready? Let's sing fist first. Ready? If the fist exerts a force upon the paper, then the paper exerts a force upon the fist. You did better. You did better. Okay, but you need work. Okay? Why does this work? What is the song asking you to do?
Response.
It forces you to identify 2 objects, doesn't it? Okay? You've got to identify the 2 objects that are interacting. That's like the key thing in Newton's third law. If you can't identify the other object that's causing the force, there's a good chance the force you are thinking about doesn't exist. We'll get to that later. Second reason that this works. Why are you never going to forget this? The emotional trauma of having to sing in public, right? Will forever sear this into your brain, right? I did not come up with this song. I did not invent it. I was exposed to it. I went, that right there, right? Maximum emotional trauma in class, physics, let's go, right? So you'll remember, and you'll come up to me, right? And you'll, Mr. Bailey, that's a hard problem. And I'll just look at you and go, right? And you'll just go, right? I literally have heard students during exams, right, like they're just singing it to themselves, right? Okay, as they work on a problem. Cause you're just trying to remember, How much math have you seen today? 0, right? Newton's laws are ideas, okay? They're ideas, they're statements about how the universe works. And attaching a fire extinguisher to a wagon, nothing bad could happen, right?
The spray from a carbon dioxide fire extinguisher looks a lot like the exhaust of a rocket. And like a real rocket exhaust, the escaping CO2 can accelerate a large mass. We'll use this extinguisher mounted on a rolling wagon to accelerate a person to suborbital speed. 3, 2, 1, blast off! Engine cut off.
What two objects pushed or pulled on each other that made her go?
Was it the contents of the fire extinguisher pushing away from the nozzle?
Yes. A lot of people want to say something like the ground on the wagon or something like that, right? Did the ground push on the wagon? Well, yeah, it's holding up the wagon, right? Because gravity wants to pull it down, okay? But that's vertical. We want horizontal stuff, right? So let me ask this question a different way. Would this work in outer space where there's no air? Yes. And now I know how many of you have seen the movie WALL-E. WALL-E. Spoiler alert, WALL-E dies. But he really doesn't. You know what scene I'm talking about? He's in the escape pod and it's been launched out of the ship, right? And boom, right? And Ava's there and she's right? And then WALL-E comes flying out of the wreckage holding what? A fire extinguisher. This is not Pixar magic. This is physics. Because WALL-E, wanting to go this way, is pointing the fire extinguisher which way? Backwards. Because WALL-E knows that if the fire extinguisher pushes some carbon dioxide out, do we need to sing the song? Right? What is the carbon dioxide going to do? Push back. No air required. Just one object pushing another object and then that object reacting. When rockets are launched, what are they pushing against? Not gravity. What does a rocket push against to go up? Not itself, can't lift up itself. The fuel. It is an explosion directed down, right? The rocket's fuel ignites, that fuel gets pushed down out of the rocket's engine nozzles. And what does the fuel do? Pushes it up. Isn't it so easy to want to run to, well, the rocket pushes against the ground or it pushes against gravity? Well, where does gravity come from? The Earth, right? So those two objects are the rocket and the Earth. But the Earth doesn't make the rocket go up. The Earth wants to make the rocket come back down. That's the hard part, right? Okay? And so the rocket pushes its fuel down, and the fuel pushes the rocket up. Pointy end up, flamey end down. That's the beginning of rocket science. Newton's third law. You can't pick yourself up. Forces always involve two objects, and we better be able to name what those objects are, and if we can't, then we're either inventing forces or we're doing something wrong. And then we get to the second law. No math in this class for 40 minutes. And here it comes. I write Newton's second law a little bit funny. Your book will write it various ways, but the standard way that most places you'll see this, okay? I write it like this. Like that, okay? And this force over here, it's either a net force, or a lot of times, I'll usually write this as the sum of all forces. You guys familiar with that capital Greek E thing? Okay. That means add everything up. Or a net force. The total sum of all the forces acting on an object. Is gravity acting on me right now? Yes. But if gravity were the only thing acting on me, what would I be doing? I'd be in free fall, but I'm not in free fall, right? So there must be another force that's acting on me. And it's the force of the floor, right? Because I'm in contact with the floor, right? I'm pushing down on the floor is pushing up on me. The earth's pulling down on me, I'm pulling up on the earth. The net force on me, the total sum of force on me is 0. And how do I know the total amount of force on me is 0? For everybody in the room is going, well, you're not moving? That's not right. Newton's second law has no motion in it. What's not there? What is motion?
Velocity.
It's velocity. What is in Newton's second law?
Acceleration.
And what is that? It's change in motion. And so I know that the net force on me is 0 because my motion isn't changing. I cannot stress enough how important what I just said was. Because you come to me with years and years and years of so-called experience in physics, confusing motion with change in motion. It's still in your brain, this idea that velocity and acceleration are somehow the same thing. They are not. Can something be moving and not be changing its motion? Give me an example. Car with cruise control, right? Okay. It's got a velocity, but it's not accelerating, it's not speeding up, slowing down, or turning, right? Yeah.
Planes and autopilot counts.
Yeah, planes and autopilot. Anything that has an acceleration of 0 also has a total force of 0 acting on it. Does that mean there are no forces? Are there no forces acting on your car when you're driving 60 miles an hour with cruise control on? No. You got gravity, you got the road, you got air resistance, you got the motor pushing it forward. There's lots of forces. But what do we know about all of those forces added up together? And why are they 0? Because the acceleration is 0. Because the change in motion is 0. So don't fall into the trap. Oh, well, it's not moving. It must have no force. Change in motion. That's what Newton's second law is telling us. I choose to write it out like that. And you're like, well, Mr. Bale, that's no different than this one. You'd be surprised that many people believe that those are two different equations. Okay? But Newton's second law sets the relationship between force, change in motion, which is the acceleration, and a new thing. Mass. What is mass? It is not the weight of something. Because weight is a force. Okay, let's dive into that. We'll get back to my earlier question. Okay, so what state is something in when only gravity is acting on it? It's in free fall, right? So according to Newton's second law, that force of gravity, okay, would be the mass of the object times a very special acceleration. For free fall, what do things accelerate at? 9.8, little g, right? Okay? So an object's mass times the acceleration due to gravity, if this is the only force that's acting on this thing, right? And is it accelerating? Is the object changing its motion when it's in free fall? Yes, okay? So I know that this must be the force of gravity acting on that object. In other words, this is the object's weight. The weight of an object is the force of gravity that acts on it. Fortunately for us, we do not have to throw ourselves off of buildings to find our weight. What do we do to find our weight? We step on a scale. All right, how many objects are interacting? If Mr. Balogh exerts a force upon the scale, then the scale exerts a force. There's two objects there, right? Why am I pushing down on the scale? Too much dinner. Gravity's pulling down on me, but that's the interaction between me and the earth. Does the scale need to be there in order for gravity to work? No. But the earth's trying to pull me down, and the scale is trying to hold me up. So we're interacting too. That force, as long as my bathroom is not accelerating, which I guess kind of depends on several factors, including how good a time you had last night, right? As long as my bathroom isn't accelerating, then the number the scale tells me for the push and pull we are giving to each other will match the force of gravity, as if I were in free fall. You can actually, so if you've ever been in an elevator, walk in the elevator, push the button, elevator go up, right? What suddenly happens as the elevator begins to go up? What do you feel?
Pushed down.
You feel heavier, don't you? Right? Like you really shouldn't have had that hop. Right? And then as the elevator gets to the floor and starts to slow down, then what do you feel? Oh, instant diet. You feel lighter? Has gravity changed? Just because no. What's changed?
The acceleration of the elevator, the velocity.
The velocity changed. You went from 0 to some speed, and then some speed to 0. So you were in a frame of reference that's accelerating, changing its motion, which means there had to have been a net force somewhere. And as you start that elevator going up, the net force is in what direction? What direction are you changing your motion? Up, right? And so it's impossible. If your motion is changing, there are no balanced forces. Gravity's pulling down, doesn't change its strength, which means the floor of the elevator must have pushed you up with more force than gravity pulls you down. And you're sitting there going, Mr. Balogh, what are you, huh? Nobody thinks like this. Now you do. This is what I'm asking you to do, okay? We're gonna unpack a lot of these examples. I'm throwing a lot of stuff at you, and we're gonna start getting, as in case you haven't noticed, into the mathematics. Newton's second law is the mathy one. The other two are statements and ideas. The idea of this one is that the more mass something has, the more force it needs to accelerate it. Sure, but that didn't help, right? Explain anything that's going on. But back to my original question. What is mass? So if it's not weight, weight is the force of gravity, what's mass? Atomic weight? No, it's still weight.
I'm about to say something about the combined something of atoms, but I don't even.
No.
Object times velocity.
An object is a quantitative measure of its inertia.
Ooh, quantitative measure of its inertia. Did Google come up with that?
No, this is in
It was in the textbook?
the pre-election notes.
Oh, pre-lecture notes, even better, right? what is a quantitative measure of inertia? What was inertia? Yeah, it's the fight against something, right? Okay, now a change in motion is an acceleration, right? But if we wanted to measure this inertia, mass is probably the best thing that we've got to be able to do that. Because something with more mass will have more inertia. Why is it harder to push a car than it is to push a bicycle? The car has more mass, more inertia, but also more mass. What has more mass, an elephant or a mouse? An elephant. You know what mass is. You experience mass all the time. It's making sure we disentangle the concept of mass from force. That's important here. But I still ask you, what is mass? I mean, quantitative measure of inertia is still is circling and not landing. What?
Isn't it how much matter an object has?
No.
The scalar?
It is a scalar. Nick?
Just like an answer anyways.
Of course I am. But I've trapped you. You can't tell me what mass is because you don't have the words for it. Let me give you an example. Okay, different example. Let's pretend, and this is going to be a stretch, I'm sure. Let's pretend that I am from a different planet. On my planet, my species, we cannot smell or taste anything. We just don't have the chemical receptors for doing that. So I would like you Earthlings to explain to me in words what salt tastes like.
Well, it has nothing to do with salt. They don't really have it's hard. They didn't really have like a definition for mass for a really long time, right? Like mass was just like a thing, right? It's like you just gotta know it in there.
Mass tastes like salt.
Right.
How do you know what salt tastes like? Because you experience it, right? So what do you know? How do you know what mass is? You experience differences in masses between objects, right? So you have a internal experience with mass. You work against your mass every morning trying to wake up. The mass of your fist hits the mass of your alarm with varying rates of speed. Right? Like you know how the interactions of mass work, but we, until about 8 years ago, did not have a definition for what mass is. It was one of the biggest kept secrets in all of physics. We don't know, we know how to use it, but we can't tell you where it comes from, why it exists, all that kind of stuff. With the discovery of the Higgs boson, we now know mass is the result of the interaction of particles in the Higgs field. Did that help? No. For physicists, it was very profound, and we handed out Nobel Prizes for it, because it helped us understand where mass comes from. But if you don't know anything about quantum mechanics and quantum electrodynamics and field theory and all that kind of stuff, it just sounds like a bunch of gibberish. So for us, we won't worry about Higgs bosons or Higgs fields or any of that kind of stuff. Mass tastes like salt. In other words, you can't give me words to explain what that is. We can only experience it. So through our experience with mass, we're going to disentangle mass versus weights versus all that kind of stuff. All right. Reasons for why I write it backwards will be made clear a little bit later. But let's see how you are doing with all of these ideas.